Hello and welcome back to Calculus 1 section 5.3 on fundamental theorem of calculus. Yes. So this is a short theoretical section where we learn fundamental theorem of calculus. It will be expanded on later on in Calc 3. Now this is going to be part 1 and part 2. Part 1, you already know. Definite integral a to b of f of x dx is any antiderivative capital F of x computed from a to b, which calculates as f of b minus f of a. This is what we did last class. So first part of fundamental theorem of calculus is the way to compute what we call definite integrals. As an example of this, we can quickly calculate 1 to 4 of, let's say, x squared minus 3 dx. And the way you would calculate this is you would find the antiderivative of x cubed over 3 minus 3x, and then instead of putting plus c, you are going to put the vertical line, which is read as computed from 1 to 4. Then you are going to plug in 4 cubed over 3 minus 3 times 4, which is your first. That's your f of b when you plug in the upper limit, 4. And then you are going to subtract 1/3 over 3 minus 3 times 1, which is the lower limit. So you plug in 4 into antiderivative, minus plug in 1 into antiderivative. So that's 64 over 3 minus 12 minus 1/3 plus 3. Please make sure that minus and minus give you plus, right? Rather than messing up algebra and losing points for no reason. Well, you lose points for a reason there. 64/3 minus 1/3 is 63/3. Minus 12 plus 3 is negative 9. 63 divided by 3 is 21 minus 9, and the answer is 12. So this is what your final exam question, whatever part A, is going to look like. You just plow through a calculation just like this to get value at the end. No context to it. No right word problem or anything, just plow through calculation to show. You guys are going to have first chapter of Calculus 2 to be applications for definite integrals. You will find volume, surface area, length of the curve, and a whole bunch of other cool stuff using definite integrals. But that's chapter 6, right? The first thing you learn in Calc 2. Right now is just faceless calculation. So doing this is your first part of what we call fundamental theorem of calculus. Now we get to the part 2, which you haven't seen yet. And this one is the interesting one where we spend bulk of our time. The derivative of the integral a to x of f of t dt is equal to f of x. This is the core of everything. So you have f of t dt. Now you know you can have any variable you want. And you have f of x. Awesome. Can anyone tell me what is this actually saying? You know, the way it's written and, you know. Can anyone figure out what this means?
Derivative of the integral is time.
It's the area under a curve between a and x.
If you call that area under the curve and you get a number, when you differentiate the number, you will get 0, right? But then this is f of x.
Change.
It's something very, very easy and basic. I mentioned it already when I taught 4.9, but let's see if you can figure it out. What does this essentially say? Like, very simple, 5 words. F of t equals f of x. That's getting there, but I still need the concept.
You're evaluating only the x.
Yes! 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 Derivatives and integrals cancel each other out. They're opposite operations of each other. Just like addition and subtraction are opposite. Now, these guys are operators. They're not operations. Operations combine numbers. So you use operations to add numbers, to subtract numbers, to divide numbers, right? That's operation. Addition, subtraction. Operators change functions. Derivative operator changes x squared into 2x. Integral operator changes x cubed into x to the 4 over 4 plus c. So these are operators, and this formula simply says derivative and integral cancel each other. Derivative and integral cancel each other. No, each other is one word. Derivatives and integrals cancel each other. Yeah, 5 words I said, right? Good. Each other is one word, right? To my knowledge, it's one word. Is it? I had my fingers moving slowly. You have to understand that everything is slow motion over here right now. 3.5 hours of sleep, 2 nights. Let's go. So this formula simply says that if you are to cancel this, you get that f of t equals f of x. Now you're going to say, hold on, t and x and so on. Yeah, that's okay, because remember that you get to plug in, and there's your x that will. So we are going to do that calculation right now to prove that this is actually what's happening. So let's calculate the derivative of integral of f of t dt. Well, we are going to start with the derivative there. What's the integral of a function? It's the antiderivative, capital F. And it's going to be of t, which computes from some number a to value x. So now we copy the derivative again, and we plug in x, so we get capital F of x minus capital F of a. When you take the derivative of antiderivative, you get original function, so that's f of x, minus 0, which is f of x. So this thing basically says that derivatives and integrals undo each other, which you knew before because we learned derivatives and antiderivatives. Well, if something is pro and anti, they just cancel, right? Just like that one example you guys had with the inverse sine of x squared. Do we remember that troll question on the test?
Yeah.
And then we had pages of answer where you can just strike those two and just say, oh, just x squared, 2x, move along with life, right? So when you have function and its inverse, right, they undo each other. When you have a number and the additive inverse or multiplicative inverse, like 2 times a half, that gives you 1, or 2 minus 2, that gives you 0. Now, the same deal happens here, because what you have is you have the derivative and integral literally canceling, and now this is just what we call a dummy variable right over here. T, you can put any other letter you want, and then when you plug in x, you see where the x kicks in. So this means that any integral that is posed in this form will just technically change the variable, and you're done. So say the derivative of integral 3 to x of cosine t dt. What's the answer? Cosine? No. Guys, what is this saying? So what is the answer? If the input is cosine t, the answer is cosine x, exactly. Because cosine is going to go into sine, right? And then when you take derivative of sine, it goes back to cosine. It's just Control C, Control V, and then you swap the variable. It's that easy. But we are not really interested in this calculation, because calculation is pointless. We are interested in the fact that fundamental theorem of calculus says that the derivatives and antiderivatives are opposite of each other. They cancel each other out. So if you have integral of the derivative or derivative of the integral, they cancel, just giving you the function that it's inside. Right? Guys, this is literally equivalent to this. Do we understand each other, right? They undo each other. That's it. Okay. Now, as every good 5-year-old, I'm going to ask, why? Why does this work?
Like
magic.
Because I told you so.
Oh, there we go. Because I told you so. That's it. We're done. The other answer was magic. Okay. What else can we master here?
Aliens.
Aliens, Russians. Okay. Russian aliens. Okay.
From wizards. Russian alien ghosts of Russia.
You mean Russians that are not naturalized? All right.
I don't know, man. I mean, like,
All right. Yeah, that's the Calc1 class for you. What are you gonna do? Maybe it will help if I write the Riemann sum and the limit definition of the derivative. F prime of x is the limit h goes to 0 of f of x plus h minus f of x divided by h, and the Riemann sum for the integral a to b of f of x dx is limit n goes to infinity summation 0 to n of f of xi times delta x. These are the two formulas which you guys have seen in Calc1, like one you saw last class, and this one you saw at the beginning, right? Lecture 5 or something is when you saw that one on top. Why do these two undo each other? What is so obvious? What do you mean opposites?
One's a derivative, one's an integral.
Yeah. Why are they undoing each other? That's the question. Says the president of the math club. Yeah, keep pushing it.
Is it because one of them is going to 0 and one of them is going to infinity?
Perfect. There we go. We just started, right? New president of math. So we started. That's just the beginning. Okay, great. One limit goes to 0, the other one goes to infinity. Fine. What else? Yes.
One multiplies, one divides.
Nice! That's a division. That's a multiplication. What else?
One more?
Yeah. There is one more that it's obvious and one that is hidden. So let's pair that one. One is addition, one is subtraction.
There's more. Are we looking at
And there is one hidden.
Is it delta x? Is it the change? Because one's change and one's measuring change or something, right? Something like
You are very close.
There's
It is the delta x. Something with a delta x. We gotta. Wow. No one ever got that far. That's the one that is hidden that no one ever got. No, we're talking about equations here. So we have the black pair, which is division and multiplication. They're opposite. We have the red pair with the 0 and infinity opposite. We have the blue pair, which is subtraction and addition are opposite. And there is one more that is hidden. Yeah, there was something that it's opposite. Yeah, but you kind of have to dx. What's the formula for dx?
Minus x.
What's the form?
X2 minus x1. Change?
Okay. So we have two forms, right? We have x2 minus x1, or we have b minus a over n, right? What do we have in both of these? Subtraction. And what do we have here?
addition.
Yeah, that's the one that escapes. But that's okay. You're still green. With these concepts, you will get better. Do you see that these two formulas are complete inverses of each other, right? If you compare the colors over here, those formulas are complete opposites. So integration undoes derivative undo integrals. That's it, right? And that's what fundamental theorem of calculus teaches us. I am still going to add that one sentence which says that area under the curve, which is part one of the theorem, is not necessarily equal to the value of the integral if the function dips below. We had those problems in there. So we're just going to add that into this mix, and that's it. We're done with 5-3. So, okay, that's why they're opposite. And now I'm just going to say, remember, just let's go as a note. If f of x dips below x-axis, area is not equal to the value of the integral a to b f of x dx. Not equal. And I believe we did we do the example last class? With did we do example for it? Now I gotta go check. No, we haven't done the example, so we can do it now. Awesome. All right, so last class we learned that we can calculate area under the curve, and fundamental theorem of calculus part 1 calculates that area. Now, if I have a basic function, let's actually set up the scenario. You are tutoring, 4th grader math, and the area of the rectangle comes up. And you have a rectangle that it's, let's say, 4 units tall, and then 6 units long. And you quickly say, oh, the area is just A times B over here. In our case, 6 times 4 equals to 24. And the kid goes, why? This is the time to immediately work out area under the curve. Here is why. Come on, you're paid. So you have to answer the question. So listen. If we have our coordinate system x and y, you'll eventually learn about that. You have a function y equals to 4, which is the constant function. And in pre-calculus, as you will eventually learn, you can write f of x equals 4. So that's your function. You want something so that's 4 tall. And then you are going to go 1, 2, 3, 4, 5, 6 units and break it off at 6, so you have 0 to 6. So now, as we learn in Calculus 1, area, if the function is always above x-axis, is equal to integral 0 to 6 of f of x, which is 4, dx. Now, antiderivative of 4 is 4x between 0 and 6. And then we know from fundamental theorem of calculus, which computes definite integrals, that you are supposed to plug in the upper limit and then minus 4 times the lower limit, getting your 24. And there will be no further questions because it's clear now. So this is how you fix things that are not broken. Right? Now,
Now the kid doesn't want to take math.
I thought that was a really good explanation. Yeah, I think that was really well done.
yeah, see? When I do things on a 4th grade level, everybody's on board, right?
I'm picking up what you're putting down. I'm only 3rd grade. I didn't really understand it, but I appreciate it.
All right, now, let's spice this up. So this kid eventually gets to pre-calc 2 and then... Yeah, I know, right? Oops. So now, question is, area under sine x on 0 to 2 pi. Right, that comes up. The kid remembers what you showed 6 years ago. Make the room, right? Area is equal to the integral sine x 0 to 2 pi dx. Let's talk about it, right? What's the integral for sine x? Obviously, pull up the phone, take a look. It's negative cosine. X computed from 0 to 2 pi. The kid remembers you are supposed to plug in the upper limit first, minus plug in the lower limit. You have to double up on those negatives there. Since the kid is in pre-calc class now, then knows that, right, cosine of 2 pi is 1, so you get negative 1 plus, and the cosine of 0 is 1, and everything comes to a screeching halt. What do we got? 0. We know it's wrong. Right? It's a good time to start crying, because when you graph sine function from 0 to 2 pi, there is an area that you can color. Right? But your calculation said that there is no area that you can color. Right? So now we see the issue. And this is the reason why I had that written in blood up there, that if the function dips below x-axis, value of the integral is not equal to the area. So do you all have that sentence in our head now? Do we all see that this calculation gave us a garbage answer? Because I'm looking for the area under the curve and I got 0, yet I'm able to color, right? So I know it's wrong. I know it's wrong. So how do I fix this? Well, we have to use the property of definite integrals, which allows us to cut the range, right, anywhere, and just add them. So what do you want to do?
Yeah, so I was going to say, instead of calculating for 2 pi, you should calculate for pi.
Nice!
Hell yeah.
There we go.
Yeah, you
So
get it done, man.
what you do is you cut at pi. And what do you do with the second integral? You add it. Good. And is there anything else that you have to do to it? So first integral from 0 to pi will be added to the second integral pi to 2 pi, but we have to do something to the pi to 2 pi integral. What do you think? Great. How do you turn? That's perfect. Turn it upside down. How do you turn this bump up? What would make negative y's into positive y's? Nope. Nope. No. Now it's getting.
Destroy it all.
Nope.
Photoshop.
No, we can do something, guys. We do something to the whole expression there to make it positive because it's below. No. That's the one. The boss.
What did he just say?
Absolute value. Yes. All right. Cool. So, yeah, it's legal. Look. So we take our sine x dx from 0 to 2 pi and break it into 0 to pi sine x dx plus the absolute value of integral pi to 2 pi sine x dx in absolute values. Great. Go ahead, compute these, and let's see what we get. You better be non-zero, right? Because both bumps are now up, right? And it should not give us a 0. Need water.
What, for the first part? For sine, for pi, and the sine x dx? You get 2. Pause. Add that to the big absolute value. Is that right?
So you will need to know.
Oh, wait, that's sort of. Oh, from pot. Oh, that makes a lot of sense actually.
Well, you're integrating this, right?
It makes
You're
so
not
much
taking
sense.
derivatives. So, so then.
It's like just switch the genre and everything.
So you have the upper value subtract from the lower value.
What did you get?
1 plus. So, wait, so what did you get? I'll show you what I did.
Someone's clicking like they want to take Jacob.
Is this the right one? Okay, yeah. So first thing, I already had this equation, so I just transferred it over. This is for.
All right, what is the answer?
4.
4. Okay. 4?
I'm hoping.
Wow.
I hope.
Awesome.
I don't think that's right at all, though.
Why? Because we are dealing with sine and cosine and you're expecting to have some multiple of pi, right?
I just,
This is one of my favorite results of calculus. Right? You push all of this trick together and the answer works out to be 4. It's like, really?
wait, is that actually the answer?
That is the answer.
Holy heck, that's wild.
So, great.
Solved the Da Vinci's Code, bro.
No, you solved the area under the curve. What do you?
Oh, yeah, like, same thing, bro. Come on.
So,
Give me a
all right, we have negative cosine x computed 0 to pi plus absolute value another negative cosine x computed from pi to 2 pi and closed absolute value. So now we have negative cosine of pi minus negative cosine of 0 plus, yes, Chewbacca, negative cosine 2 pi minus negative cosine of pi. There we go. It's a lot of negatives and stuff. Cosine of pi is negative 1, so we have negative 1. Minus and minus gives me plus, and a cosine of 0 is 1. Plus absolute value. Cosine of 2 pi is 1, so we have negative 1. Minus and minus gives me a plus, and then cosine of pi is negative 1. Negative 1, that's a 1 plus absolute negative 1 minus 1. And I was about to give you the best password ever. You just use ones, capital I's, lowercase l's, zeros, zeros and O's. That's it. You should write it on a paper for someone. So here's the password. I used to do that when someone used to annoy me for my MATLAB homework. It's like, oh, I missed the homework. Can you open it just for me? I say, sure. It's when I have a password. So I write the password with negative 1, with ones, lowercase l, capital I's, zeros and O's on a little paper. Here you go. If you figure out 6-digit code, the Da Vinci code, right? It was a unique code. And I didn't come up with that on my own. I actually, one of my Rotaract friends from DC has that as a pay license plate.
Wow,
eyes,
so genius.
yeah, eyes and ones. So you go through something and the camera catches like, what is this? 1, 1, 1, 1, 1. Nope. So go figure it out.
That's genius.
I know, right?
So kids are smart, man.
It doesn't work on anything. So. You gotta sit there and figure out what is the actual legitimate plate.
Was it 1, 1, I, or L, 1, or was
No,
it
you don't have lowercase. You don't have lowercase on place. So it has to be eyes and ones.
Wow. So close.
Or you can do zeros and O's.
Imagine like a police investigation lasting for like months just trying to crack that. It
Trying
could be
to
so
figure-
many different things. What is going on?
All right, cool.
That makes sense.
So I hope that this example is sufficient, right, for us to understand that when we go below x-axis. Are we cool there? All right. Now, I have to go back to 5.2 because I used the property which I forgot. Well, we didn't have time to finish, so I never wrote the properties. I need to write 3 properties. So I'm going back to 5.2. If you have room in your notebooks, go back to 5.2 and add these 3 formulas because these are properties of definite integrals, and we just used one of them, right? In this, we just used one of them, so I just need to add these in where they belong. Properties of definite integrals. Property number 1 is going to say that if you have definite integral a to a of f of x dx, answer is immediately 0. Would that make sense? Yeah, because there is no rectangle there. There's no function, right? I mean, there is a function, but there is no width, because a equals a, and when you plug in, you're going to get f of a minus f of a. It's dead, right? So that's the first property. The second property is the one, and you are going to encounter this in Calc 2 and when you start doing U substitution in 5.5 as well. Guys, sometimes when you do U substitution or trig substitution coming up, right? When you do substitution and you change your limits of integration, you are going to end up with a bigger number in a lower limit and a smaller number on the upper limit, which is backwards. And now you were wondering, can I actually flip them? The answer is yes, but you have to put a minus in front of the integral. So if you run into a situation where you need to flip a and b, and I usually use the different color here so it stands out. See, b is now on the bottom and a is on the top. I really need to make that pop so you can see it. So if you need to swap the limits, right, because you have the now, again, does this make sense? Yeah, just think of it that it's equal to capital F of b over here, capital F of b minus capital F of a, right? And over here, what do you have? Negative capital F of a minus capital F of b. So when you distribute the minus, you get the one on the left, right? So they are equal. I know. All right, property 3 is the one I used in the other example, which says that you can break your interval of integration anywhere between a and b if you need to. And we had to, so we can flip the function. So integral a to b of f of x dx is integral a to c f of x dx plus integral c to b f of x dx. And the easiest way to understand that is if you just draw a picture of some function and you have your a and you have your b, and now you have some arbitrary c somewhere. Doesn't have to be in the middle, can be anywhere you want. I'll move it more left now. There we go. And that creates your area 1 and area 2, because now you have two separate integrals, and this integral here will give you area 1, and this integral here will give you area 2, and if you add them, you get the total area. You can break it up 17 times if you need to. This skill will be used again for improper integrals in Calculus 2. You absolutely need to know. You can live without 1 and 2. It's just going to be a lot of calculations for you for no reason, right, to get the same answer. But number 3 is going to be crucial for a section on improper integrals in Calculus 2. So make sure you know this one moving forward. All right, so that's it. We plugged in the whole from 5.2. We're done with 5.3. Next one is 5.4. Learn 3 formulas there.